Welcome to lesson 5.4 on randomness and probability. So just to open with a little simulation, suppose that four friends get together to study at Alex's house for their next test in AP Statistics. When they go for a snack in the kitchen, Alex's 3-year-old brother makes a tower using their textbooks. Unfortunately, none of the students wrote their name in their book. So when they leave, each student takes one of the books at random. When the student returned the books at the end of the year to Hirsch, the students were surprised that none of the four had their own book. How likely is it that none of the four students ended up with the correct book? So what we would do is on 4 equally sized wooden chips, we would write book 1, book 2, book 3, book 4, shuffle the wooden chips, and randomly place one on each of the squares. We would check to see if the book matches the student number. So book 1 does belong to student 1, but did it land there? And so we would try to see if 0, 1, 2, 3, or 4 students got their own book. Okay, and if one of those, whichever value that was, 0, 1, 2, 3, or 4, okay, then we would write that value in for each round, do 5 rounds of shuffling your little wooden chips and laying them down randomly and seeing how many students got their own book. And then we took the tallies out of the whole class, and it seems like there was 8 groups in the class, and 8 times 5 is 40, and we found that 15 out of the 40 trials, that 0 students got their own book, and that is 0.375, so there's about a 37.5 chance, according to our short simulation, of this happening, of no students taking their own book. Okay, there's another Rossmann chance applet here that's kind of a popular applet among teachers, and it's the same idea. 4 babies get mixed up at the hospital, and the parents randomly choose the babies to take home and which baby is going to the right house. Luckily, things like that don't quite happen. What is the law of large numbers? If we observe more and more repetitions of the same chance process, then the proportion of times that a specific outcome occurs approaches a single value, which we call the probability of that outcome. The law of large numbers just tries to talk about how you do need more and more and more repetitions, and then you start to approach the probability. So after just 40 trials of putting the chips on the different persons, student 1, student 2, student 3, student 4 box, and trying to see how often 0 students get their books, then we are not doing that many times. The law of large numbers says that you really have to approach like millions of trials in order to start to observe the true probability. Okay. All right, so I'm gonna skip this just for the video's sake. How do you interpret probability? Probability is a number between 0 and 1 that describes the proportion of times an outcome of a chance process would occur in a very long series of repetitions. Probability of 0 means that it was absolutely impossible to have occurred, and probability of 1 means it's a guarantee. So if I say draw a card, Nikki comes up and grabs a card, she got a card. It's a guarantee that she got a card. It is impossible that she rolled a die. Okay? She wasn't given a die to roll. So 1 means it's a guarantee, 0 means it was impossible to occur. Beware of scientific notation in the calculator. If you get this kind of answer, 1.03, that is not a probability. Probabilities are between 0 and 1. There's no such actual thing in mathematics as having like 103% chance of something happening. So look all the way down the screen to see what the scientific notation is, and then move the decimal that many times. It's really 0.0103. Okay? All right. The probability of getting a sum of 7 when rolling 2 dice is 1/6. Interpret this value. So be sure that you are looking at it as a very long run series of repetitions, okay? And that idea of the law of large numbers is that we need more and more repetitions of the same chance process in order to start to observe probability. So we say if we roll 2 die many times, that's key, then the sum on the 2 die faces will be 7 about 1/6 of the time. No guarantee, because it's very hard to actually observe that perfect probability in the real world. It would take us millions and millions of rolls, and many times we don't have time for millions and millions of rolls. Okay, so that's called theoretical probability. Okay. Imagine you are flipping a coin. Write down the results of 50 imaginary flips. So I just went at it, right? Heads, tails, heads, tails, heads, tails, all through, and I just grouped them up in fives just to make it easy to count them. So 50 imaginary flips, okay? Next thing, find your longest streak of heads. So I took all the heads and I thought there's one, two, two, and I thought, okay, I've got a streak of 2. Now I've got a streak of 5 and a streak of 2. So a streak of 5 in a row was my longest streak for heads. Okay, write that number here. Make a class dot plot of each student's longest streak. And here's my students' longest streaks. 4s, 3s, 5s. Okay, lots of 4s and 3s maybe. Okay. Just fewer 5s and 3s. Okay, so essentially 3s, 4s, and 5s we had a lot of, and one person had a 7. Okay. Compare the distribution of longest streak for students with the distribution created by Fathom. Okay, we'll get there later. Okay, so which of the following outcomes of a coin flipped 6 times is more probable? Heads, tails, heads, tails, tails, heads, or tails, 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 heads, heads, heads? Both are equally probable. Okay, so what we're going to say with that is that the order and the streakiness in the short term, just 3 and just 3, is really not remarkable to us. Okay, and what we would have found in the Fathom plot here is that it's actually quite probable and a little more common than you would think to get a streak. So when we think of randomness, we sometimes think of chaos, even with our with a data set, and we think that that looks more genuine than that looks. Okay, as far as a run of heads and tails goes right in a row. But streaks are more common than you would think. Okay. What are some myths about randomness? We cannot apply the law of large numbers to a small number of trials, especially for probabilities close to 0 or 1. We will not observe probability in a short number of trials, fewer than 10,000 trials. The law of averages is a fallacy that addresses this. It means that the next outcome must be something to balance out the previous. So if you had tails, 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 tails showing up, then people would believe the next one would be more likely to be a heads. Okay, this happens too. Have 4 daughters. The father wants a 5th baby. It will still be a 50% chance of getting a girl. Okay, the 5th baby unborn doesn't know what the previous genders of the children are and how many there are of each. Okay, the next child is just going to be what it is. All right, so coins, dice, cards are all chance processes. They have no memory. Okay, trials only balance out in a very long run sense. This law of averages is stated all the time in sports, especially by the announcers. They say, oh, Johnny's got a hot hand tonight. He's getting all the 3s. Okay, and there's a belief that he's going to continue getting 3s. Okay, well, that's a little bit arguable because we don't always think that that sports is random events like coins, dice, and card draws are, but we think that sports, there's a little bit more of mental game going on, and if you're getting your 3-point shots, you're going to continue getting them a little bit more likely because of your positive flow you've got going on, okay, and like in your head. But yeah, so we hear law of average references a lot in sports, and someone saying like, oh, well, he made all those shots, now he's destined to miss one. Okay, Joe DiMaggio's hitting streak. There was an interesting discussion of the hot hand in an article in the New York Times, March 30th, 2008, written by Samuel Arbesman and Stephen Loaf. Okay, in the article, the authors claim that one of the most remarkable streaks in baseball history, Joe DiMaggio's 56 consecutive game hitting streak, was actually not very remarkable at all. Obviously, it is extremely unlikely for any particular individual to have a hitting streak this long. But when considering all the players and all the seasons in baseball history, we should expect some very unusual performances every now and then. To investigate, they simulated the performances of every baseball player in every season, a total of 10,000 times. In each of those 10,000 simulated histories of baseball, they recorded the longest hitting streak. In this simulation, in about 42% of the trials of the simulation, someone had a hitting streak of at least 56 games in a row, with the longest being an amazing 109 games in a row. So that's a really great example of a streak, okay, generated by a computer that was told to randomly give people hits and whiffs based on their batting averages, okay? And so when you program in the batter's batting average and you give them all their at-bats, sometimes there's amazing streaks, okay? In casinos, there is often a large display next to every roulette table showing the outcome of the previous spin of the wheel. The result of the previous spins reveal nothing about the results of the future spins. So why do casinos pay for these displays? The casino knows that many people will be more willing to place a bet if they observe a pattern in the previous outcomes. As long as people are placing bets, the casino is making money. So if the casino shows that there was a streak of 3 red or 3 blacks on the roulette wheel, then maybe someone is more likely to sit down quick and bet on red, okay? What is the purpose of simulation? Yeah, if simulation is not the true theoretical average and we believe in the law of large numbers, then why do they have their place? The purpose of simulation is to estimate a probability when it's difficult to calculate it theoretically. What are the 4 steps? Do you need to do the 4 steps in each simulation? Yes. You have to state your question of interest. You have to plan, describe the random assignment process, mention what is to be recorded at the end of each repetition. You have to perform multiple repetitions. Then you have to conclude. Use your results to answer the question. Statistics problems demand consistency. Suppose that a basketball announcer suggests that a certain player is streaky. That is, that the announcer believes that if the player makes a shot, then he is more likely to make his next shot than if he missed that previous shot. And as evidence, he points to a recent game where the player took 30 shots and had a streak of 7 made shots in a row. Is this convincing evidence of streakiness, or could it have occurred simply by chance? Assuming this player makes 48% of his shots, and the result of a shot does not depend on the previous shot, how likely is it for the player to have a streak of 7 or more made shots in a row? There are 2 explanations. This player really is streaky, or isn't streaky and it was just chance. So, our statement is, what is the probability that a basketball player who makes 48% of his shots makes a streak of 7 or more shots in a row out of 30 shots? So let's number. We're going to number 00 to 47 to denote the player making the shot, and 48 to 99 to denote the player not making the shot. That way we have 47% of our possible digits that are, 48% of our possible digits that are going to be, indicating a shot and indicating a miss. Okay, and that's correct for his shooting average. Starting at a random line on the table of digits, reading left to right, 2 digits at a time, until you have selected 30 2-digit numbers. Record the number of times you get a streak of 7 or more digits, meaning the digits 00 to 47. In a row with a check mark, and if not, with an X. So I did line 125, and I was able to use all the digits that I came across. So 96 is a miss, 74 is a miss, 61 is a miss, but 21 is a make. 49 is a miss, and so I went through and I underlined all the makes, and I got a streak of 3 in those 30 shots. So my longest streak was 3 shots in a row. So I went through each line on the table of random digits, and I asked my students to come up with how long the longest streak was, and I kind of divided and we divided and conquered, and we did this only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times, but that's all right. That's a short number of trials, and we got a streak of 4, 4, 3, 4, 3, 6, 4, 4, a streak of 7, a streak of 3, and 5 as our longest streaks in each of those simulations. So our simulated probability of a basketball player making 7 shots in a row when shooting 30 shots is about 0.083, because it's 1/11th of our trials that resulted in a streak of 7 or more. What are some common errors when using the table of random digits? A common error is not mentioning your labeling and keeping your labels of the same size and the same and as few digits as possible. Not mentioning that you're reading left to right, how many digits you're reading, and not mentioning all the specifics of what you're going to do to mark a success and a failure. Okay. Suppose I want to choose an SRS of size 6 from a group of 60 seniors and 30 juniors. To do this, I write each person's name on an equally sized piece of paper, mix them up in a large grocery bag. Just as I'm about to select the first name, a thoughtful student suggested I should stratify by class. I agreed. We decided it would be appropriate to select 4 seniors and 2 juniors. However, because I already mixed up the names, I don't want to have to separate them all again. Instead, I will select names one at a time from the bag until I get 4 seniors and 2 juniors. This means that I may need to select more than 6 names. Okay. Design and carry out a simulation using Table D to simulate the probability that you must draw 8 or more names to get at least 4 seniors and 2 juniors. Okay. So what is the probability that you must draw 8 or more names to get 4 seniors and 2 juniors? Label the 60 seniors 01 to 60 and the 30 juniors 61 to 90 using a random digit table, reading left to right 2 digits at a time, skipping numbers outside this interval and repeats until you have 4 seniors and 2 juniors. If you draw 8 or more names, mark the trial with a check. If not, mark the trial with an X. Then repeat this 3 more times for a total of 4 trials. Find the probability of selecting 8 or more students from the grocery bag. So the first time, I needed to select 1, 2, 3, 4, 5, 6 students. The next time, I needed to select 11 students. The next time, 8 students. The next time, many more students again. So in our class simulation of 4 trials, 2 trials took 8 or more selections to select 4 seniors and 2 juniors with a probability of about 0.5. Okay, when working with a random digits table, students often make mistakes and do not clearly communicate the method they are using. Remember, every label needs to be of the same length. If labeling 1,500 items, the labels should be 0001 to 1,500, not 1 to 1,500. Also, if you are not using all the labels of a certain length, then explain that the remaining labels should be skipped or ignored. Finally, if the process involves sampling without replacement, then clearly acknowledge that you will ignore repeated labels or look for a certain number of unique labels. Okay. So here's just some examples. If you have 100 digits that you want to choose from, label them 00 to 99, because by using 00, you get to then just use 2-digit numbers. If you have 1,230 in your total group and you're trying to find them, then go 0001 to 230. And if you have 390, go 001 to 390. Okay? what are some key parts to include in the plan step if you are using each method? So the hat method, you must put all the names in the hat on equally sized slip of paper, shake well, and draw one at a time until you have selected 10 names or whatever. Using technology. Using my calculator to randomly generate 5 numbers between blank and blank, I got these numbers. Calculator can generate numbers like 1, 2, 3, and 2-digit numbers like 10, 11, 12, and 3-digit numbers like 200, 201. So don't use a phrase like this, counting 2 digits at a time. Also, don't number like this, 0, 0, 1 to 320. Just label 1 to 320, okay? You don't need to talk like you're using a table of random digits when you're using a calculator. Okay, and how do you use a calculator? Go math, probability, randint, min, max. So min is like 1, max is 300. N is your sample size, so I want to choose 10 individuals. Okay, or randint, no repeat, then go 1 to 300, but it only spits out one number at a time. Oh, that's it. It lists all 300 values with no repeats, and then you would just take from the first 10 values. Okay, thank you for joining me for 5.1. I'll see you for 5.2.